Thank you all for coming today. I didn't realize that it would be so many of you, but that's really awesome. What I talked about before starting was instead of doing something purely geochemical as a geochemist, have over the course of many years gotten very into hyperspectral technologies, which are a natural, we'll say, cousin to geochemistry because it's all mineralogy. And if you don't have a fundamental understanding of geochemistry, you can't really appreciate as much of what you start to see out of hyperspectral. There is touches of geochem in here, but then I have a little outline after this, but then we'll also get into a little bit of 3D modeling. We'll get into some machine learning stuff, and we'll learn a bit about the Atacama Desert along the way, which is in Chile, where I lived for about 5 years. So all this will be fun, I think. The title of the talk that we're going to do today is called Size Matters, the Importance of Mineralogy and Texture in Mining Porphyry Copper Deposits. And we'll come back to this theme a bunch of times. With this, I just want to acknowledge that some of the people that went into building this talk over the course of many years, and that would be Cristal Palafox, Julio Palomino, and Tom Carmichael. Oh, it looks like, hold on. I just want to set this up so I can see if somebody has a question, because importantly, yeah, okay, I got this. Importantly, as we go, if anybody has questions, I just want you guys to ask them. Raise your hand or shout at me. Both work perfectly fine because I like having things more interactive, as opposed to just waiting till the end. I think I just don't have enough space on my screen, but we could do something where you maybe drop it in the comments as well. Yeah, here's the chat. So yes, you can drop in the comments, or just raise your hand and I'll try and I guess firstly see that you've raised your hand. And secondly, if I pronounce your name incorrectly, I'm very sorry. Please just let me know and I will try to correct that and learn on the fly. I'm just very grateful that you guys have asked me to be here. So thank you so much for that. So today's plan. What I wanted to start with, because as we're an SEG student chapter, is just to talk about first some basics about hyperspectral and like the fundamental actual physics of it. As geochemists, we're naturally afraid of physics, but in this case, it's not really geophysics. So that way it's not, fake news or anything. And then also before we take a break, which I put it for about 10 minutes, but I guess it depends on all of our timing, but I think 2 hours is quite a long time, especially to be talking online. So just at least 5 minutes for everybody to get up and to walk around. But before we do that, I'll have the background of the background geology of the area. We're going to be looking at the Antucoya mine, which is in northern Chile. We'll have a map for that too, because I can imagine it's a little bit far for you guys to be very accustomed to where Antofagasta, Chile is, which is the region that it's based in. And then we'll do a little quiz, which is more just to promote discussion than to actually quiz your knowledge. Break, and then afterwards, what I'm calling part 2 is really just a workflow that I've been working through for quite a long time now, which involves both hyperspectral point data, but also hyperspectral imaging data, some machine learning, and some 3D modeling. So here we'll look at some hyperspectral data from the Antucoya mine. We'll look at it, just what the data itself looks like, so you guys can be familiar with that. Plus, it's really fascinating, very cool. We'll do some unsupervised learning and then 3D modeling with that hyperspectral data, then some supervised learning with the data, and then a summary of going back to the beginning of like why I named the talk the way that I did, of why size and spectral parameters are important. And we'll just finish up with a little quiz. And again, not to necessarily test your knowledge, but just to promote some discussion. So nobody be afraid. I am the champion of asking very basic questions, because if nobody asks the basic questions, how do we get into stuff that is much more, can be deeper questions from that. So any question you have at any time, I really welcome. And with that, I think we'll get into it. Let me just admit one more person. Okay. Okay, so the physics of spectroscopy, or what we're going to say here is hyperspectral basics. Spectroscopy, just really quick, is the broad umbrella term for, and hyperspectral falls under it. Hyperspectral is just a piece of a spectroscopy. You can have multispectral data as well. Hyperspectral just means that there are a lot of bands of information, and we'll get into what that means as well. So it's just a subset of spectroscopy. So understanding the basics of spectroscopy is what we're going to be doing now. Some of the pictures that I have up here are either going to be my own, or they'll be just stuff that I pulled from the web because I didn't take a picture of something that maybe was slightly interesting about the Antofagasta region. The Antofagasta region in Chile is, you can think of it as like a state or a province. It's far to the north in that country. And it's fascinating in the sense, most of Chile is, in the sense that you can either be at sea level, or within an hour, you can be in the high Andes, which are over 5,000 meters tall. So this is a volcanic range. This is the Andes, and they look very small, but that's just because we're already at, I think, the Flamingo National Reserve that I was at, which we couldn't walk through because it was already snowed through, but they look so small because we're already at 4,600 meters of elevation. So anyway, it's very humbling to be there and very beautiful. So why would you use hyperspectral in a program? Something I like to think about all the time, and I never want to knock core logging geology because there is a definite role for what core logging geology can do. But one thing that we're not very good about as humans is being able to be reliable and consistent about the identification of mineralogy. And I'm not necessarily talking about, can you identify a grain of perhaps chlorite, which may be easier than some other things to identify. But something that hyperspectral is very good at is particularly identifying clay mineralogy and some different sulfate mineralogy. And we're going to get into this, especially in this case study, which is why I mentioned them. And these ones are almost impossible to identify with the naked eye. Sure, you might be able to identify gypsum, but to be able to distinguish kaolinite from montmorillonite, from saponite, from nontronite, all these things have really, really important roles to play in the metallurgy of a project. So why do we do it? There are many reasons, which we're not going to all get into today, but I think most importantly, if a project has consistent and reliable mineralogy, especially from the beginning, but it can be at all stages. But if we do it from the beginning, then all future applications from exploration through to the end of mine life will be easier to anticipate. So from an exploration point of view, you have surface, you can do soils, you can do rocks, you can do it during drilling, whether it's diamond or RC. RC, reverse circulation, very difficult to identify mineralogy. And you can start to build alteration models from the beginning, which is not necessarily typical. During resource assessment, you can put this information into block modeling, which I'm doing with 2 of my own projects right now. You can use it to help with to select your preferred methodology to extract your ore of interest. You can also use it for geotech. Mining, you can use it in development, ground support, infrastructure, blasting, caving, pre-processing, during processing, comminution, extraction, recovery, end of life. You can use it in your tailings or in your environmental studies. So there's lots of ways in which you can use this throughout the entire cycle of a mine. In terms of the data analysis itself, all it is the process of transforming raw spectral response data into mineralogical or geological information. And if you're using images, it can include both images and numerical data. Otherwise, it can just be the numerical data. The actual interpretation of the data is highly specialized, and I would argue that it is the combination of mineralogical and geologic knowledge that is going along with the appropriate software and computing capacity that's going to give you the best results. But there are other ways in which people use less of this kind of second line of what I believe is the most important. Okay, so what is spectroscopy? It is the study of the absorption and emission of electromagnetic radiation, in other words, light, by matter, and it's measured as a function of wavelength or frequency. It's a tool for characterizing the structures of atoms and molecules. And don't worry, we're going to get into all of this. And they can either be obtained as the results of the absorption, which is typical more of the Vernier swerve, or the emission of light. Excuse me. So here we just have a schematic for electromagnetic radiation. Your emitter, it can either be, let's say that you're running, let's say that you're outside, you're running a airborne survey, you're using satellite data, you're using point data. Your emitter could very well be the sun. Otherwise, we'll talk about preferred lamp sources, but you could be using a quartz halogen lamp, say in a scanning system, and that's going to be your emitter. It's going to emit the electromagnetic radiation to your sample, which will, in our case, will be some sort of geologic material, whether it's soils, whether it's coarse rejects, RC, diamond drill core. We have a lot of different things that we do in geology. And to be really simple to start with, you're going to have the resulting spectrum that will come out of this, that will go into your spectrometer, and you will have a readout that will give you some squiggly lines. I wanted to take a quick stop over here to just talk about just the actual mechanics, really, of what's going on inside of a spectrometer, just because the more I've gotten involved with technology and mining, the more I recognize the power of understanding not just the final product, but what's actually happening inside of an instrument, whether it be a hyperspectral spectrometer, whether it be XRF, or a ton of other things that we have going on right now in mining. What's really important from your light source is that you are understanding that there are photons that ultimately are going to be reaching your detector at a very specific wavelength that are going to be converted to electrons via the photoelectric effect, which, if you forget about Einstein, don't worry, we'll talk about him in a few slides. But these electrons at the detector itself are then going to be converted to a voltage, and this voltage will then be digitized, turned into a number by an analog to digital converter. And then each of these values is then going to be tallied and summed into your final spectral signature, or that little squiggly line. Your final product is going to be in radians. And I say this also because that's another important thing that we'll talk about in our next slide, because it's important. Let's not get too excited too quickly. So really what's happening within your whether it's a TerraSpec, whether it's another similar style of point and shoot, whether it's an airborne spectrometer or a hyperspectral scanning spectrometer, these instruments are measuring radiance, which is a function of wavelength. Spectrometers overall, they comprise these different optical components, which would be your light sources. You have different types of optics, which would be lenses or telescopes. You have beam splitters. You have diffraction gratings. You have mirrors. You can either have single detectors, detector arrays, multiple detectors, depending on the design of the instrument. That is to say that these things, you're not just going to, unless you're some sort of genius, and I don't want to preclude that, but you're not just going to go and develop a new piece of tech in your basement, right? Like these things take a lot of planning. There's some very complicated engineering that goes into it. And that said, if you're interested in these things, I know these kinds of engineers, and I would be happy to let you in on, some contacts so that you guys could, maybe you don't want to do geology, maybe you want to design things like this. Who knows? Okay, so this slide looks really boring because it's black and white, but the most important thing that we're seeing here is where we have our radiance, which is squiggles that look like this, and see these little panels, which we'll come back to, and we're converting it to reflectance, which looks fairly similar to this, except into here where we start to see these actual, what we're calling absorption features that look much more similar to what you will start to see in spectra that we'll see in this presentation and maybe that you've seen previously. The reason that I put this in here is because, as we talked about in the last slide, all of our spectrometers are collecting data in radiance. However, it needs to be converted into reflectance. And so the way in which you do this is to use these panels called spectral panels. If you're working in a more advanced system, they might have these really dark or different degrees of dark panels. But typically, if you have, say, a teraspec in the field, or again, some kind of point spectrometer in the field, you will be seeing these bright white spectral panels. Also, if you see scanning systems, you'll see them. If you ever see them not bright white, that is a huge problem because it relies upon this being completely clean, no dings in it, no fingerprints, because it needs it to be a perfect reflector. Without it, you can't make a good calibration. So when we calibrate, this is to prevent shifts in absorption features, and that's relevant with whatever type of spectrometer you're working with. A question that you want to ask your providers when you're talking with a scanning company is, how often do they calibrate? Because if the answer is we don't calibrate, which I have heard before, or not often, then that's problematic, because one of the really interesting things that we can do with this type of data, and maybe you've seen it in papers before, is you'll see people that talk about, okay, I was in this porphyry and I saw this white mica wavelength shift from muscovite to phengite, or from paragonite to muscovite, or something similar. And this will be, when I was in looking at paragonites, I saw no grade. As soon as I got into muscovites, I saw some grade. And then when I got into phengites, I saw all my grade. And so we have developed some different ways of looking at these wavelength data that help us determine whether or not we have proximity to grade. There's no rule for it necessarily. Every deposit I've ever looked at is different, but there is some kind of framework around it. And we have these wavelength shifts for more than just white micas. There's probably 8 or so minerals that have different wavelength shifts that you can calculate. So if this is off because your spectralon is dirty or not being calibrated often, then you might have drift, and this kind of calibration might not be real. So we're going to talk slightly more about it in the next slide, but it's so important to have these clean panels so that you can convert basically your raw data that you get from the actual spectrometer itself into data that we use in order to interpret. And this is just looking at the fact that spectrometers are generally prone to drift, especially if there is different temperatures. I work in a lot in Arizona. In the mornings, it's very cold. In the afternoons, it is very hot. And that cycle goes on repeat. And sometimes it's often out of the range of the of what the instrument says that it's okay with. So that's even worse. So this is just an example of just, at 0 hours at 20 degrees Celsius, and there's just, more or less everything is fine. But then you can start to see how over the course of 3 hours without calibration, how there is some drift in in the response. So it's just a very important question that just to ask your providers about how they check for instrument drift, if they calibrate often, because we just want to make sure that the instrument is accurate. One thing also that some providers might have, in addition to Spectralon to do the actual calibration, is they might have, say, this is just a NIST rare earth standard, which has, and these are the different absorption features that are occurring at very specific wavelength features. And if they hit every single time, then you know you're good. If they don't, and they're moving around, then you just have a failure because you know that your instrument is drifted. If there's drift in your instrument, it's not to say that you can't say that your general mineral groupings are incorrect. You'll the kaolinite is a kaolinite, a chlorite will be a chlorite, etc. But to say that you can use your chlorite wavelength shift, then is probably incorrect and should be discarded. So in terms of the physics of light, this field is constantly evolving. The wave theory was really important. Quantum theory from Planck was really important. And then something that's used to this day in how spectrometers function actually is the photoelectric effect, which is Einstein. And that's to say that these energy packets or these photons interact with matter by liberating electrons from the atoms that make up the matter. And it's, as I said, one of the principles of modern day remote sensing and spectroscopy, whereby light interacts with surface atoms, liberating electrons, which we then are measuring with our detectors. So in terms of spectroscopy, what we're trying to say is, namely, what is light and how does it travel from point A, which would be our emitter, how does it travel from there to point B, which would be our surface material, and then what happens to it once it gets to point B. And so basically what we're just trying to quantify and what we're trying to understand to make sure we give you the best result possible is, how do we go from this piece of rock to saying that it has biotite and chlorite, which we know because biotite and chlorite have specific absorption features in specific areas, as well as you can also, depending on the software you're using, quantify things like shoulders, slopes. There's a lot of different things that you can use to quantify these things. But all of this is possible because of all the basics that we just talked about. All of this is electromagnetic energy, and EM is just referring to all the energy that moves with the velocity of light in a harmonic wave pattern. And these wavelengths are divided into discrete ranges. So this over here is what we see in terms of every day, the visible light. A lot of these companies that you work with will incorporate a bit of the visible light into their interpretations. And then you have the near visible infrared that's occurring more or less over here, the shortwave infrared that occurs between, in this diagram, between say 1,000 and really up to 2,500 nanometers, midwave and long wave. In this presentation, we're more so going to be talking about the near visible and the shortwave infrared. So we'll be focusing really on these areas. And so when we think about it, like, how is this, we're just looking at all these physics terms and everything. And so how can we ask, how is the EM spectrum relevant to us? And the easiest way for us to see it right now, I think at this point, is just to say that in terms of, okay, here's the visible, here's the infrared. And we just looked at here's the near infrared, here's the short wave, mid wave, long wave. Well, if you have hematite in your deposit, that you're going to use the veneer for. If you have some porphyry, that is going to be identified in the short wave. If you have garnets, you can work in the veneer to some extent, but also maybe much more effectively in the long wave. So all these minerals have different locations in the different parts of the infrared. Some of them span multiple parts of the infrared. Some of them are only focused in one part of the infrared. Like I said, we're going to be focusing on this talk mostly in the veneer SWIR and perhaps mostly in the SWIR, to be honest. This was a great image put together by CoreScan many years ago. And this just looks at where the different, well, I guess action is really happening. So here you have the veneer, here you have the SWIR. In general, here's your chunks. In terms of the physics of what's happening, you have electronic absorption features that occur more or less up to 1300 nanometers. And afterwards, all of what you're identifying is based on vibrational absorption features. And when you look at different minerals, there's very specific regions where specific things are occurring. So, here you'll have if you have an absorption feature that includes, unbound water, if it includes aluminum hydroxide, if it includes carbonates, they're occurring in these specific areas. And that's how these spectral geologists are able to identify specific minerals. The fundamental measurement that our spectral geologists are using is obtained in a spectrum. So this in total will be called a spectrum. And all this is a plot of measured infrared intensity or energy returning to the spectrometer versus the wavelength of light. So you can see here that we have reflectance, and here you have wavelength. This over here is a tourmaline spectrum. And you can see that there are, in this one in particular, that there are features occurring in the veneer with iron 3+, iron 2+, and then you have a bunch of features that are occurring in the shortwave with hydroxide, water, and then aluminum, magnesium, iron, and boron hydroxides. And it's like a fingerprint. For each mineral that is identifiable and a part of the infrared, it is specific to them, and there is no other mineral that will share all of their characteristics. Like we talked about before, in terms of that energy or these light sources, for these scanning systems, you're using quartz halogen lamps. You can also use it for handheld or lab-based instruments. Why specifically quartz halogen? It's because they provide a continuous light source that follows a Planck curve, which, do we need to know that? Maybe not, but it's kind of interesting. But then for other things like remote sensing, we're using solar light. And then to an extent important for the thermal infrared or the long wave, you can use also Earth's emitted energy. This, I think, is one of the slides that I like the most because it drives it home for me. So if you have a white object, it is a perfect reflector. It will, all the colors of the rainbow go into it and are reflected back. If you have a black object, it is going to absorb all colors of white light completely and equally. And then just to kind of drive home what happens during what we're calling absorption and what we're really using to identify all of these minerals. So what happens is you have this incident energy that interacts with a material. For example, in this leaf over here, you have all this white light coming in. Some energy is absorbed. So really, most of these colors are going to be absorbed by this leaf. And then the wavelength that's reflected, in this case, the green light, is the color that we observe. And this occurs for all things. This is the principle of why we see specific colors. So what happens to light when it interacts with a mineral surface? Some light is going to be reflected directly back to the detector. The absorbed light and really this energy is going to interact with the molecules in the sample material. So maybe we can think of this as maybe a piece of drill core with lots of different minerals in it. And then the interaction of absorbed light will change the energy of the molecular bonds, either by causing changes in the electronic energy or vibrational energy of this molecule. There's also rotational energy that occurs in longer wavelengths, but we're not going to talk about it in this talk. So this would be an example of what's happening with vibrational energy. So if, let's say that this is a calcite. Was that a question? Maybe not.
It's okay.
Oh, wait, is it okay? Okay, thanks. All right. So vibrational effects. This is honestly in a calcite crystal. This is one of the things that's actually occurring. How it's just moving around like this. Okay, so like we said, what we're going to talk about today, electronic and vibrational energy. And sorry, that got me thrown off. Let's move to the next slide. So what's happening in the veneer? That these electronic processes are captured in veneer. You have here, and so a good example of a veneer spectrum would be magnetite, which is an iron oxide. It has this very broad absorption feature around 1100 nanometers. But what's happening here is you have this photon coming in, you have this energy coming in. The absorbing energy is going to initiate this reaction whereby electrons within a target molecule may be excited to other energy levels or orbits or shells. These are really high energy and are going to create broad absorption features like this said magnetite spectrum. If this is occurring between about 380 and 750, this is actually visible light. So these are some of the things that we see. And these are going to reflect the color of the mineral. Doesn't happen with all of them, but this is something. They can also be related to other electron movements and behaviors, such as electron charge transfer, color centers, or these S centers, crystal field transfer, and electron transition. In terms of the SWIR is going to measure the frequency of molecular bond vibrations in the sample material. These bonds relate directly to the chemical makeup, nature, and geometry of molecules in the material that's being analyzed. And these are characteristic diagnostic, providing a fingerprint for different minerals. This vibrational energy is very well documented, very well understood, and occurs in predictable ways. You have things that are occurring in perhaps stretching vibrations, different types of bending vibrations. Like we said, it's all incredibly well understood and documented, and that's why we can say this spectrum is a perophyllite, this is a tourmaline, this is a etc. Because physicists that have come before us and chemists that have come before us have really battened down and figured out why these are occurring and where they're occurring exactly in the electromagnetic spectrum. Okay, so finally, the combination of these electronic and vibrational absorption features will result in this diagnostic spectrum. So here is something that came out of a hematitic shale that can identify minerals in the sample material. Basic mineral identifications are generally made by a comparison just to a reference library, of which there are a bunch that are out there available for people to download. Okay. Does anybody have questions about these like basic physics principles? We are now going to talk about the different things about your spectrometers itself. Spatial resolution, spectral range, amount, quality of spectrometers, and the amount of pixels. I see we're at 10:50. We started at 10:15. I'm going to try and do this in about no more than 15 minutes. We'll see how she goes. Spatial resolution. Basically, would be from a Landsat, so about 30 meters pixel resolution. This is from the Vera satellite, 20 meters resolution. The HIMAP airborne system, 3 meters resolution. This is from the core scan hyperspectral scanning system at 500 microns. This is a piece of drill core. So really what we think about is pixel size, but really it's defined as the smallest object that's clearly imaged within distinct boundaries. Spatial is probably the easiest thing to understand because I think we think about that, daily, maybe. But what is spectral resolution? I think that's a little bit maybe trickier to understand because most of us don't spend our days looking at spectra. So this would be reflectance over here, like we looked about. Here's wavelength. We're looking at just a specific absorption feature here. And so this would be we're looking here at the 1400 nanometer feature. Basically, if you have something that is very coarse resolution, you might not even see something that's very high resolution that maybe is actually really important. So over here, we're looking at really what looks to be more of just like a doublet over here. Two things that are really important in identifying perhaps a talc. In this very coarse resolution, are we seeing it? I don't think that you can see it perhaps until you get to something around about here. So it's typically referring to how wide each of these bands are. So band being where you have a specific feature occurring. What's really important about understanding spectral resolution is if you are looking for a specific mineral, are you able to identify it with the system that you are going to be using? If you're really interested in wavelength shifts, is the system that you're using, is it too coarse to be able to show you a really nice, say, white mica chemistry change? If you're using a Landsat satellite, it's definitely not going to be able to show you that. The new NMAP satellites, which have hundreds of bands, will be able to show you that because they have very high spectral resolution in terms of satellites. If you're going to be using a scanning system, asking them how many bands they have, asking them the spacing of the bands, are they covering the area that you want to see, are all very good questions. So this is just another example of what that would look like in terms of if you're working in multi-bands, maybe over here you get, so this would be more, say, looking like a Landsat satellite. And so you get, I think that has 7 different areas where they have absorption features. If you're working with something like the NMAP satellites, which were just launched only, I think, a year, 2 years ago, now you have hundreds of bands, and now you're starting to get something that looks like a real spectrum where you can start to identify not only specific minerals, which you couldn't do in Landsat, but also perhaps some chemistries. So this is just another way to look at it. So this would be your Vera satellite. This is covering a really complete range from V near through to the SWIR. If you're using Aster, you have a few bands, these guys right here in the V near. You have some that are occurring here in the SWIR, and then you have some in the long wave. So the question really becomes, are you going to be able to resolve in an area the mineralogy that you're looking for? Are you going to be able to, if looking at Gaussons are important, can your satellite identify those? If you're really focused on mapping SWIR features, your Landsat maybe isn't the right answer. Maybe you want to go look for NMAP. This one I'll do very briefly. Typically in scanning systems, you'll have a Venier and you'll have a Swerve spectrometer. There's one out there right now that has three, I believe. I don't think there's more than that. Somebody correct me if they know differently. But it's just basically to say where you have overlap is preventing you from where you might have some really noisy areas, particularly when you get out to here. In this region over here is where you're identifying your amphiboles, your biotites. There's some chlorite features. Anything that's mafic is hanging out over here. Maybe if you just have one spectrometer, that's not going to really help you. But if you have a company that has an extra spectrometer, maybe you'll get some better spectrum that will help you in those areas. You also have to ask them too, though. I know this is a lot of information, but maybe some of this sticks. But something that's really important is asking them how they are co-registering their data. Are they collecting all the data separately? Are they doing it in separate paths? I mean, it gets really complicated, but the point is like, can they combine the spectrum into one or no? Signal to noise, this is just how much energy or signal a company's putting in versus the amount of background or instrument noise. This noise could be due to poor calibration, poor detectors, optics, bad illumination. There's a lot of reason why you can have a lot of noise. But if a company has really high signal to noise, you should be getting, a really crisp picture like this. If they have really bad signal and noise, why are you even bothering using it? So asking these questions is really helpful. I threw this one in here. It's one of my favorite slides overall because it just goes to show that this type of data, the whole goal is producing a spectrum. All of these different all of these different instruments are they're all related. Point systems, these ASDs, these teraspecs, these halos, they're producing spectrum. As are if you have a line profiler system like a HiLogger or Veracio, core imaging, there's about 5 or 6 companies on the market that are offering core imaging services. You have things, Hyperspectral, that can identify mineralogy and outcrops. You have airborne companies. There's 2 of them, I believe. Drones have been a big thing on the market. And then you have satellite imagery. All of these things talk to each other, and you can invent programs that are based off of learnings from a different part of this ecosystem. Okay, to sum up this section, it's really just to say, why would I want to use a point system versus a line scanning system versus an imaging system? One of those reasons would be the idea of increased counting statistics. So perhaps in a point, in this case, we've identified that we have phlogopite. With a line system, so this would still be your point column. Here would be a line system. Now we're identifying, because we have, say, 20 spectra in total along this line. Now we've identified we have a little bit of calcite, but we have mostly chlorite and phlogopite, and we have a little bit of white mica. However, when you move to a scanning system, what you're now seeing is all this texture. And within this texture, so in this instance, now in this area, we have 55,000 points in total, spectra in total. Now we're seeing more minerals. We're seeing how they occur. You're not necessarily seeing completely, say, a paragenesis. It can help with that. If you have these very trace minerals that have big impacts for whatever stage of the mine you're in, it can be really helpful. Nowadays, and we'll talk about this when we're going to talk about our unsupervised learning, the other thing that's really important is that these images are also data that you can use to extract textural information that can go into modeling. So there's both the visual component of why they will be important, and then there's also now the machine learning data science part of why this will be important. Okay. Do you guys want me to do an introduction of the Antiquoya mine now or after our break?
It's better after break.
Okay. So then, because I know you asked for it, let's do a quick quiz, which I've never done before. Quick quiz. What are questions that you should ask hyperspectral vendors and why? I knew this was a bad idea. Nobody likes to talk. Don't be scared. What's one question that you would ask a vendor? I honestly would ask a vendor, most importantly, I think, would be if they're calibrating, to be honest. I would ask them how they're
I remember
calibrating.
that you said about the calibration that it should be usually rechecked because in 3 hours its calibration was unstable.
Yeah, so TerraSpec recommends that you calibrate every 15 minutes. I know of hyperspectral providers that are calibrating every core box. There are some other ones that are calibrating twice a day. It's a good question to ask, and it kind of shows the knowledge that they have of their systems as well if they answer you. The other question I would ask is, let's say that you're in an iron ore deposit. I would ask if they had a veneer system, because the veneer is the only part of the infrared that's going to help you with iron oxides. If you were in an epithermal area, I would ask them about their SWIR, because that's where they're identifying all of your clay mineralogy, which is going to be really important. I would ask to see examples of their work, to be honest, as well. The last thing that I'll ask, and I will just help you guys out with it because I see that we're shy, which is fine, it's just, should you collect data everywhere? And really, deposit style, is it mineralogically appropriate? Is the system that you're asking to work in an area going to help? So, for instance, people might say if it's magmatic nickel, then can you really help? Those rocks are really dark. I know of hyperspectral providers that have done great work in these types of systems, but I don't think that all of these companies are qualified to do it. So deposit style is important. Also, what question are you trying to answer? Do you have questions about exploration? Do you have questions about metallurgy? Do you have questions about carbonates in mine closure? There are companies out there that are suited for everything, and there are some that are suited for very individual things. So ask yourself what you're trying to answer, and that will help. And then lastly, do I need to scan every single piece of core or geologic sample? And the answer to that is probably no, you don't, but constructing a very appropriate survey of how to answer your questions is going to be super helpful.